Well, hello, my name is Ruiz Aldana. I'm from the CIDEV. My ID is 1957686 and my group is 218. The name of the topic that I will discuss is the periodic motion with the concepts of frequency and period. Well, the topic, as I said, is the periodic motion, and I will talk about oscillations, period, frequency, cycles. Well, first of all, we need to conceptualize the concepts that we will study. What is periodic motion? Well, periodic motion is have two words: periodic and motion. Motion is everything that changes in is movement, and periodic is something that is repeated constantly. The definition of periodic motion is a, a motion that is repeated constantly. How we describe a periodic motion with the elements that I will explain later, that is the period and the frequency. But an example of a periodic motion could be this cable turning around over and over again. Now that we know what is a periodic motion, we need to establish what is a cycle. For example, in this pendulum, when I have a periodic motion, a cycle is the part of the movement that is repeated over and over again. If this cycle in this periodic motion, the movement is circular. Each time that the pendulum passes through this point is one cycle. 1, 2, 3, 4, 5, 6, 7. Well, now that we know what is a cycle, the cycle, the length of the cycle isn't measured in meters or in something of longitude or another quantity. A cycle is measured in time. I will explain why later. But the time that takes to a periodic motion to complete a cycle is the period. For example, if for this pendulum takes 1 second to make one cycle, we can say that the period of this pendulum is 1, because it takes 1 second to complete one cycle. Now, the frequency. The frequency is calculated with the period. The period and the frequency are inversely proportional, and I will explain in the mathematical concepts why. The frequency, to conceptualize what is frequency, is the number of oscillations. An oscillation is the same as a cycle. 1 oscillations, 2 oscillations. Well, a frequency is the number of oscillations over a unit of time. With more oscillations are more frequency. The unit of time is practically the period, because it's the form that we have to measure a cycle. So the number of oscillations over the time take the period of the oscillations is the frequency. If the period is 1 second, and in 1 second we do 3 oscillations, well, the frequency is 3. If we do 1 oscillation in 3 seconds, with a period of 3, the frequency is 1/3. Well, now let's make some math. We have the period. The concept of period is the time that takes to a periodic motion to make one cycle. So the variables that we have is cycles and the time. Well, let's try it. Period, time, cycles. Well, in here we have the three variables: period, time, and cycles. For example, we have that period is represented by a t, time is represented by a lowercase t, and the cycles, well, are represented like cycles. Let's make some proportions. Is the period, and we have time. With more time, more period. So we can say that the period is directly proportional to the time that takes to do a cycle. We have it in here. Period is proportional to time. Now, period, how it relates with cycles? Where? Suppose if we have more cycles in a specific unit of time, that means that there be less time taken to do one cycle. Yeah, if there's more cycles, it will take minus time. So we can say that the period is inversely proportional for the number of cycles. How I write it here? 1 over the number of cycles. Period is proportional to time, and period is inversely proportional to the number of cycles. So when we have the proportions, the unique thing that we need to do to make a mathematical formula is to multiply the proportions by a constant. The constant that we will use is 1. So we could have that the period is equal to the time over the cycles, that the number of cycles that we are measured. The total time over the number of cycles that we are measured. Well, now let's and makes a lot of sense with the concept that is the time that takes to a periodic motion to make a cycle. If we make a division, well, the formula have a lot of sense. Now let's do what is the unit of a period. Well, we will represent period with the t. We know that the time is measured in seconds, and the cycle is dimensionless. That means that we say one cycle, two cycles, it don't have one unit. So I will represent the number of cycles with theta. That is a number of cycles. In the international system, we could say that the unit of the period is seconds over one cycle. That means that is the seconds that take to do one cycle. If we ever will have one cycle, so we can measure the period as seconds. Then we have it here. I don't know if it could be appreciated, but well. Now, let's make an example. Sorry. Now that we know all the math, let's make an example. We have a periodic motion. This is a wave. It is a periodic motion. We know that one cycle that this is one cycle and this is the other cycle, because the movement from here is repeated over and over and over and over again. So we have two cycles, and we will suppose that the time taken to do that these two cycles is 0.5 seconds. It's a lot of time to a wave, but it's just an example. So we have two cycles in these 0.5 seconds. So to calculate the period, we just do two cycles, no, 0.5 seconds over the two cycles. That is equal to, if I'm not wrong, 0.25, something like that. Yes, 1/4 of second, or 0.25 seconds. Just like that. And that's all. That's how we calculate the period of a wave or a periodic motion. But now, what about frequency? What are the variables that interact in the frequency? Well, we know that is the frequency, and the period, because the concept of frequency is defined as the number of oscillation per unit of time. The unit of time is, of a periodic motion is measured with the period. So the period is in this is interacting with the frequency. And we also have the number of oscillations, that is the same as cycle, but we will put oscillations. Now let's make proportions with these three variables. First, we will represent frequency with an F, period with a T, and oscillations theta. Why? Because there is a number of oscillations. So frequency. The frequency, let's make a proportion between frequency and period. With more period, with more time taken to do a certain number of oscillations, with more time, for example, if the oscillations are, let's take one oscillation, theoretically, with more time taken to do that oscillation, with more time taken, there will be less oscillations per unit of time. So the frequency will be lower, theoretically. So the frequency is inversely proportional to the period. We have it here. Now, let's make a relation between the frequency and the number of oscillations. Suppose that we have a static unit of time that is 1 second. In 1 second, with more number of oscillations, in 1 second, the frequency will be greater or higher because there are more oscillations per unit of time. So we can say that the frequency is proportional to the number of oscillations that we will represent it like theta in here. So let's make a mathematical formula multiplying again by the constant of 1. So we have that frequency, it's equal to the number of oscillations over the period. Ta-da! But now, what's next? The next that we will do is take the unit of the frequency. Well, we know that frequency it's equal to the number of oscillations that we are representing it like theta is dimensionless, so they don't have a unit. So I will represent it like theta over seconds. So the international system make a new unit for this. The number of oscillations over second have a new unit that is Hertz. Hertz for a German physicist, with the name of a German physicist that studied waves. Well, Hertz. It can be represented with an H and a lowercase c, and that's it. This is the international unit for measure frequency. Now, let's make, like in the other case, an example. We have, again, other periodic motion. But now let's draw it more small. The period taken to do all these oscillations, we measure it, and it's around 1 second. 1 second. And the number of oscillations that we have are, we have it in here, 6 oscillations in 1. The formula is frequency is equal to the number of oscillations over the period. Okay, yes, it's correct. The frequency is equal as the number of oscillations over the period of time of all the oscillations, that is 1. So the frequency is equal 6. Let's make it easier to the concepts that we already know. Period it's equal to the time to take to do one oscillation. That's right. Period is time over oscillation. So the time to do one oscillation is 6 oscillations is 1 second. So one oscillation is 1/6 of second. The period is equal to 1/6. like in here. Period is equal to 1/6. That is the time taken to do one oscillation, how we conceptualize. And the frequency is equal to this oscillation over its period. Frequency is equal to these oscillations over its period. Something like that. The oscillation over 1/6, that is its period. So we just make long division and we will find that the frequency is equal to 6. Now the form that we do is how we conceptualize. The form following just the formulas give us the same result, so the formulas are correct. For the experimentation of this project, I will make a comparison between two kinds of periodic motions. First, I will impulse this pendulum with the acceleration to gravity that it has with 90 degrees. Theoretically, with more period will be less frequency, and later I will compare it with another periodic motion of 45 degrees, and theoretically with less period, more frequency. I will measure the degrees with a transporter, and I will measure the time of the period with a chronometer. We will make the first periodic motion, 90 degrees. Okay. The chronometer. 1, 2, 3. Five seconds for 3 oscillations. Now we will repeat 3 times this process. To make an average and get the more exactly number. 1, 2, 3. 5.47 seconds to do 3 oscillations. Now the last time. One, two, three. 5.6 seconds to 3 oscillations. Now let's calculate the oscillations, or the frequency of 45 degrees. 3, 2, 1. Three oscillations in 5.44 seconds. Now again. 1, 2, 3. 5.11 seconds for 3 oscillations. For the end, for the last one, one, two, three. 5.22 seconds for 3 oscillations. And I will make the math. Well, I make all the math, and the results were that the movement, the motion that was impulsing 90 degrees had a frequency of 0.54 hertz, and the motion of 45 degrees has a frequency of 0.57 hertz. That makes a lot of sense with the proportions that we already made, because between more period, less frequency. So all the proportion is correct, and we prove it experimentally, theoretically, calculating it. So the conclusion of all this topic that I have is I could conclude that the before established formulas are correct. More specifically, the frequency are directly proportional with the number of oscillations and inversely proportional to the period. That the period is also directly proportional to the time of a cycle, and that it takes a lot of sense with the word that is frequency, with more frequency that a periodic motion takes place in the same position, well, or with the same motion, well, is more frequent. That's my conclusion, and that's my explanation. I'm Antonio Ruiz, Aldana, and it's a pleasure to be with you.